let's understand how do we solve this numerical. Guys, with support of this numerical, let's try to revise what we have studied about Colruy's law and many other things. Alright, we already have seen Colruy's law for finding molar conductivity at infinite dilution of weak electrolyte, and the equation that we had checked out was this: molar conductivity at infinite dilution for acetic acid was, we use sodium acetate, we used hydrochloric acid and sodium chloride. Now mind you, all these three compounds which are there, they are strong electrolytes, so they would dissociate, so we would have no problem finding their molar conductivities, alright, at infinite dilution. So that's what we used. Now we also saw that how in equation everything got cancelled and what we were left with was acetate and H plus ion, thus providing us with molar conductivity at infinite dilution for acetic acid. Alright, so weak acid was our requirement and what we dealt with was strong. So we could find its molar conductivity. Alright, so this we have done. Calculating molar conductivity at infinite dilution of a weak electrolyte from those of strong electrolytes. Alright, so this was our strategy that we applied for finding out molar conductivity at infinite dilution for weak acids. Alright, then how did we choose? What was the choice? The choice was, now see, this was what salt of given weak acid, that is acetic acid, and strong base. Now base, say sodium hydroxide. Sodium hydroxide and acetic acid gives you salt of weak acid and strong base. So that we chose. Then the H part which was there, that was strong acid. Alright, so we used here hydrochloric acid. Now we could have also used here sulfuric acid. Alright, and we subtracted it with salt. What sort of salt did we choose? We chose salt of this and this. Now if this would have been sulfuric acid, then we would have used here sodium sulfate. Alright, I hope you get the idea. So how to choose molecule? Weak acid, this is our requirement. Salt of given weak acid and strong base plus strong acid, alright, minus salt of strong acid, strong base. Alright, so suppose if this would have been nitric acid, then it would have been NaNO3. I hope it is clear how to choose molecules when we intend to find molar conductivity at infinite dilution of weak acids. Alright, this is what we had done. So this is recapped. Now we also know that relation between molar conductivity and electrical conductivity K, that is, this is equal to kV, that is molar conductivity is equal to electrical conductivity into V, where V is volume of solution in centimeter cube, and that's also equal to 1000 K upon C, where C is concentration. Guys, I'm just revising all these things because you would be requiring these things in numerical in some way or the other. Alright, we also know that degree of dissociation alpha in terms of moles of electrolyte is, degree of dissociation is number of moles dissociated upon total number of moles, and percent dissociation is alpha into 100, that is degree of dissociation into 100 would give us the percentage dissociation. This we would be requiring for our numerical. Alpha we also know is root of K into V, that's also equal to root of K over C, where V again is volume of solution and C is concentration of solution. Alright, now let's get into our numerical. I hope this revision helps you in giving you some idea about other numericals of these types. Okay, now let's get into our solution. In terms of moles of electrolyte, degree of dissociation was number of moles dissociated divided by total number of moles taken. Alright, now here the situation is, here it is molar conductivity divided by molar conductivity at infinite dilution. The value of which is given, it is 9.54 divided by 238. Now when you do this, this is the value you get. Now what we are interested is in degree of ionization. Now percentage degree of ionization of ammonium hydroxide, it is alpha into 100. Alright, so it is degree of dissociation into 100. So that itself is this. So this is the answer. So the answer is A.